Continuing from the last discussion, let me quickly recall. Remember, we were talking about mantle melting, and let me quickly recall the partition coefficient values very briefly, because I have given you the details before. So this value is, say, roughly K is equal to 1, and this is lanthanum to lutetium, lutetium being smaller, lanthanum, and somewhere here you have europium. And somewhere here you have europium. So I draw the line for K is equal to 1. Remember, it's a very important thing. These values are K greater than 1, and these values are K less than 1. So if you quickly recollect, then from the diagram, if without going into the magnitudes, this is what would happen to the partition coefficient values of olivine, orthopyroxene, and clinopyroxene. This is what would be the range of K values. If you take the other important mineral, garnet, then the K values would be something like this. This is for garnet. Remember, I will just give you an approximation so that you keep things in line. This is K is equal to 10. So this is how garnet looks like. As I told you, a part of the garnet, the heavy rare earths, or the ones with the smaller radius, the heavy rare earths, garnet has values greater than 1, but for the light rare earths, that means the lanthanum side of the rare earths, they have lower values. And then you have plagioclase, which is for mostly incompatible, but then you have a peak that goes up here, and then you continue this. So this is typical of plagioclase. I am not ignoring hornblende at the moment, because the dominant minerals are plagioclase, OPX, CPX, plagioclase, garnet. Remember, the plagioclase lazolites are a very small part, so you have dominantly peridotitic mantle, and as you go to high pressure, you have a garnet-bearing peridotites or garnet-bearing lazolites, or whatever that is, that the composition is. So this is what is generally the partition coefficient values. You have to remember these patterns. So plagioclase, lanthanum is higher, lutetium is lower, and at europium it is a positive europium anomaly. So this is what is called. Now I just wanted to say one thing here. In this diagram, this peak is because of EU2+. Remember, all lanthanum elements, all rare earth elements are trivalent essentially. Only this peak comes in because under reducing conditions of the mantle and the lower crust, europium, for example, it's a very reducing, under reducing condition, U2+, europium becomes U2+ is stable, and U2+ has an ionic radius very close to calcium. So what happens is there's a lot of intake of europium into the calcium side, and so you have this situation. But there is something what I call, if you had to join these two elements, if you had to join these elements, you see these are the flanking elements. My God, this pens are. These flanking elements here, if you join this straight away like this, then this will be the value for EU3+. Have you understood? If europium was in a trivalent state, then the partition coefficient value would have been continuous. So remember, you have this problem, so this is called the anomaly. Here, for example, you have europium 2+ peak here, and this would have been the value if europium was trivalent. So this is the major difference of partition coefficient values. Right? So, and this is the Garnet value with the heavy rare earth elements having greater than 1. Then I think lutetium has a value close to 6.9 or 6.6, something like that. That's the highest value, and it starts from 0.01 for lanthanum. So these are the dominant elements that dominate the mantle. And if we are talking of partial melting of mantle, then we have to take, these are the elements that should give us a clue to what's happening. Remember also that as you go down the mantle, you have peridotitic mantle, but does not contain garnet. Then as you go higher pressure, garnet appears. Why? Because from a reaction between clinopyroxene plus plagioclase gives you garnet, and orthopyroxene plus plagioclase gives you garnet. It's also orthopyroxene plus garnet gives you clinopyroxene plus garnet. So these are different assemblages. I'm not going to the details of this. This is not a metamorphic class, but those are which stabilizes garnet. But when you go higher pressure, then your olivine reverts to beta olivine, and garnet breaks down to pyroxene. This I told you before, with a perovskite-like structure. And further below, the orthopyroxene breaks down into MgO, which is periclase, and other elements like stishovite, and with ilmenite structure, calcium ferrite structure, and so on and so forth. It becomes more and more complex. So now we transfer this information in our mind to do a little bit, try and understand trace element partitioning a little bit. Now, I have derived the expression before that Cs by Cs0 is equal to 1 by, what was the expression? I forgot. That's the problem when you go extern for anyway, it was K into 1 minus F, was it? Plus F? Was it that? I just forgot. You please get through it. But the important point that I was telling you, the concentration of a particular element in the solid, or, this is Cl, or you can also find out Cs0, and this is K by K into 1 minus F plus F. You please kindly check this number. I don't remember equations. So I derived it, I derived it, I've forgotten it. I think it should be this. Now what is important is here, CIL and CIS. That is the concentration of an element in the liquid and concentration of that particular element in the residual solid. We are interested in that. What we are trying to do here by dividing CSO, we are trying to normalize it with respect to the unmelted metal. Now, if therefore you want to find out these parameters, what things you have to know? You have to know CSO. So you need to know the concentration of the mantle. You need to have an idea of the partition coefficient K. And you need to have an idea of the F, which is the fraction of melt remaining. If you know these three parameters, then you can find Cl. Also, if you know these three parameters, then also you can find out Cs. So both CIS, concentration of the element in the solid, concentration of that particular element in the liquid, can be found out completely correctly if we get an idea of the initial concentration of the element in the solid into the bulk partition coefficient into the F into F. Is it okay? Yes, right. So I got it right for the first time in my life. Right. So these are the three things you need. These are the three things you need. The concentration of the mantle before melting, partition coefficient value. If you remember, if you have to know the bulk partition coefficient, if I put a K bar, remember the bulk partition coefficient, then also what you need to know not only the mineral melt partition coefficient, but you should also know the proportion of the minerals. Remember, your K is equal to W sigma WIKI. This I explained before. So not only do you need to know the concentration of the particular element in the solid, you also need to know the mineralogy of that metal. Now that is two different things. One is you need to know the concentration of a particular element in a rock, and you also need to know the proportion of the minerals in a rock, because the proportion, weight fraction, gives you a answer to what should be your bulk partition coefficients. Have you understood? Now this is a complex topic that I'm talking about. You should know the rock. What you see today is a molded rock. You see, if you go on an earth and find a basalt, you find a basalt. What else can you find out at the maximum? You can find out a xenolith. Now the question is a mantle xenolith, an ultramafic xenolith. Now the question is, xenolith by definition is a foreign material. Xenolith by definition is a foreign material. The other word, which is the opposite of xenolith, is called otolith. What is an otolith? Otolith is a part of the whole process. Xenolith is foreign. So the moment you say the word xenolith, basically, technically, we eliminate it from the system. So, if you can say that, sir, I will analyze the xenolith, I will find out the concentration of the element of the xenolith, and I can see the xenolith, I will also be able to find out the proportion of the minerals. What is the problem? The problem is here. The problem is this material, ultramafic material, which is in your lava flow. Are you sure that that is the rock that was molten? Or is it possible that that rock was entrained in the lava flow during its ascent? Was it entrained in the lava flow when the magma rose up? Can you be sure? That is the problem. That is a huge problem. And that, finding that out requires some sort of an isotope data, may be helping you and giving you another way to approach the problem, but the problem is complicated. This you must clearly understand. That is why much of the geochemical trace element modeling is done. This trace element modeling seriously hinges on this parameter. Or else you can say, okay, so I don't want this parameter itself, I want the ratio. Then you talk about the ratio. Then you talk about the ratio. Then you don't talk about the rock that was melted. The precursor to melting, don't talk about it. You can't have it both ways. You can't have the bread and the butter on all sides of the bread. You can't have it. You've got to have a logic. You say, I want to find out this. Fine enough. No problem. You find the ratio. Don't say that I have found out the concentration of the lava flow. Don't say that. What you say then, okay, then I measure, then I'm doing something. But what you measure in a molten magma, in a lava, under a gabbro on the Earth's surface, you measure the rock. You measure the rock, you measure you measure the element in the melt. So then, what is CSL? God knows. God knows, because you were not present there in the mantle at a depth of 20, 30, 40, 50, 60 kilometers and saw the mantle melting, and you did not take a chunk out of it. They remain anonymous. You don't know. And xenolith is a xenolith. It's foreign to the process. Otolith is a part of the process. Then otoliths can be formed. Early fractionating minerals can form otoliths. Like in anorthosites, for example. Many times you find otoliths. Not that you don't find xenoliths. You find orbitals. Right. In any way, theoretically, this is going into, I'm trying to tell you the shortcomings of geochemistry. You must, when you do a work, you should not only know what your strengths are, but you should also know the limitations of your work. That makes you a good scientist. So, theoretically, if I have to know Cl theoretically, then I should, this you can measure. You can measure the lava flow. You can measure it, no problem. But CSO remains unknown. And partition coefficient, bulk partition coefficient, which depends on the mineralogy, is also don't know because you have not seen the rock. Right. And then F, even worse, you don't know how much, what fraction of how much, to what degree the mantle melted. This is pure speculation. This is pure speculation. Only thing geophysical data tells you, at the low velocity zone, you don't have more than 1% melt. Geochemical people tell that there cannot be more than 5 to 6% melting in the mantle at a particular given time, but that's about it. That's various. So you know that in the mantle you can have low degrees of melting. That's all what you know. Right. You put a definitive number in that. It has its own errors. So, now when you do this rare earth element business and trace element modeling of rare earth, you often come across a term which is called chondrite normalized. This, all of you, I am sure, have heard about it. Chondrite normalized. Or sometimes normalized to depleted mantle. These are terms which are very much used. Or normalized to primordial mantle. These are words that are quite in geochemistry. Now, I don't want to go into this depleted mantle, primordial mantle. These are all a little bit of speculation, but I would like to talk about chondrite normalized. Now, what does this mean, chondrite normalized? What is this? Essentially, this stems from a very important fact. My pens are all gone. I don't know what happened.
So you just these pens,
Okay. Chondrite normalized. Now, what happens? Say, for example, this happens. Say, if this is the number of, if this is the, say, atomic number, that means either equal to the number of protons or number of equal electrons, the periodic table, as you go this way. And this is abundance of elements. Abundance of elements. Let's say for chondrites. I don't know if you know why chondrites are taken, but I think you should know. So these are the concentrations of abundance of elements. Now, elements are there which have even atomic number and odd atomic numbers. Elements have even atomic numbers and odd atomic numbers. Even atomic numbers are those that have paired electrons. Odd atomic numbers are those that do have unpaired electrons. Now, if you plot their abundance curves, if you draw their abundances, you will have a curve for even atomic number elements and you will have a curve for odd atomic number elements. The important point here is elements with odd atomic numbers have lower abundance. Odd atomic number elements have lower abundance than even atomic number elements. Say, for example, in the cosmic curve or for the chondrite. If you actually join them, then what will happen? You will have a curve like this. Do you understand? You will have a curve. If you join it continuously over continuously atomic number element, so you will have a curve like this, where the even atomic number element is flanked by odd atomic number elements with lower abundances. This is always there. This is why it's called a sawtooth pattern. Sawtooth pattern. Now this type of pattern becomes very difficult to handle, a sawtooth pattern. It's very difficult to handle in a graph. So what happens, since most rocks have it, a sawtooth pattern, so in order to sort of flatten the curve, Masuda, a person, a Japanese, and Masuda Coriel, they suggest as a mechanism that if you have a graph like this, then divide it by a graph like this. So this will give you a smoothened curve. So that is why a chondrite normalization is done. So basically, when you divide a rock composition by the composition of the chondrite, you can see how much enriched is the rock respect to a chondrite. And that chondrite normally is a carbonaceous chondrite. It's normally a carbonaceous chondrite. And that carbonaceous chondrite, if you go through cosmochemistry, you will see that carbonaceous chondrite, the composition of the elements, except certain atmophile elements like carbon, hydrogen, oxygen, and nitrogen. These are atmophile elements. Or lithium, beryllium, and boron. Remember that word. Atmophile elements like oxygen, nitrogen, carbon, oxygen, all these elements. Or lithium, beryllium, and boron, these elements. Or hydrogen and helium. If you leave aside these elements, hydrogen, helium, lithium, beryllium, and boron, and the atmophile elements, the composition of carbonaceous chondrite and the composition of the solar system is identical. So that is the most important point. So what happens when you have a value 10 times chondrites, 10 times chondrite, this means that the rocks are enriched 10 times with respect to chondrites, or 200 times, or 800 times, whatever the value is, enriched with relative to chondrite, whatever the process is. But that is what it is. Or it could be a value which is in decimals, 0.1, with respect to the chondrite. It is from this chondrite that the Earth accreted and the solar system accreted. So this is the basic theory of the Masuda Coriel suggestion that if you have a sawtooth pattern of a rock divided by a rock which is a sawtooth pattern, so normally we do it chondrite normalized, it's very common, or somebody uses a model primordial mantle composition. These are all models. No one has got a primordial mantle, or maybe they have got some places where they think that it's a primordial mantle, but no one has sampled a primordial mantle. No one can tell you today, okay, here is the mantle, here is the primordial mantle. No one will give you that. But people, through their science, through their logic, try to argue in favor of a primordial mantle or a depleted mantle, whatever that mantle is. What is a depleted mantle? A depleted mantle is where from melts have been extracted. So a primordial mantle, a depleted mantle, the depleted mantle is from the melts have been excited. There are depleted model 1, mantle DM1, DM2, DM3. There are multiple, they call it reservoirs of depleted mantle. So you have reservoirs of depleted mantle and primordial mantle and chondrite. So you can normalize with, because of the science that you're doing, you normalize it with whatever you have. So chondrite normalized is a concentration, is a concentration term. Although you must remember, the concentration has a unit, grams, milligrams, whatever it is. Chondrite composition it's a weight divided by weight. So it's numberless. It doesn't have a dimension. Okay? So it does not have an unit. So, before we go into the details, just let us check a little bit. And keep it, I think you know this diagram now. I will keep this diagram. Okay, let us see. Say, for example, I draw a diagram where I have, say, for example, this is the composition of a mantle. Primordial mantle, I am writing. And this is chondrite normalized rock. It's called rock by chondrite. Rock by chondrite. This is lanthanum here. This is lutetium here. Somewhere it's iron here. Now follow this correctly very much. Rock by chondrite increases this way. So the values normally are 10, 100, 1000 is already very high. And these are in log scales. So 100 is here, 200, 300, 400, 500, it becomes smaller. So remember, these are all log scales. And here you will have lower values. Say this is 1, this is 10, this is 100. So this will be 0.1, 0.1, 0.01, etc., etc. Let's say I have a rock, a primordial mantle. It is chondrite normalized. Let's say I have this value. I will not take this value. I think you will be biased unnecessarily. I take a value like here. I take a value like here. This is my primordial mantle, this one. I take this value. Otherwise, you will always think that it is 1. Let me say, this is 1, of course, chondrite normalized. Oh, okay, I mistake here. Yeah, so let's one. I draw a rock, unmelted rock whose composition is here. Let's say this is 2 cm. Let's say this is 2 cm. What does it mean? It's chondrite normalized. It gives you a value 2. Let's say it has this pattern, 2. That means it is twice enriched than a chondrite because you're dividing everything by chondrite. So this is twice enriched than a chondrite. Now let's say my rock contains olivine, orthoperoxene, clinoperoxene. Now, I have already shown you the partition coefficient values. So if I do that, then I know from my memory that for these 3 minerals, in whatever proportion you take, the values will be different, but the partition coefficient value for lanthanum is lower than the partition coefficient values of lutetium, and the values are lower than 1. Have you understood? The partition coefficient of this rock containing this, the lanthanum value should be lower than the lutetium value, and both should be lower than 1. Both should be lower than 1. So that is an important point. So now, if I melt this rock, now the question, say for example, I'm giving you an idea of the bulk partition coefficient. And what is this value? This value is CS0. Remember? CS0. Because I have taken the value of the unmelted primordial mantle, say, primordial mantle is twice chondrite. That means I have assigned a value to this. And then I have taken a K value, we can do it numerically, but just for the heck of it. But I don't know what is F. I don't know what is F. But I know that F is 1. So I say if I take a value 5% melting. 5% melting means F is equal to not 0.5, it's 0.05. Okay. So I know this value, I can calculate the quadrant normalized value of lanthanum, lutetium, etc. And what will they do? Because lanthanum is more incompatible than lutetium, both are incompatible because they are less than 1, but lanthanum is more incompatible than lutetium. Therefore, the melt that is produced will have this type of a slope. The melt that you produce will have this type of a slope. Why? Because lanthanum is more strongly partitioned into the melt because it is incompatible relative to lutetium. Have you understood? And then, once that melt is there, that means I have found out CIL, so now I can also find out CS. And CS would occur somewhere here. This is depleted melt. Have you understood? Remember, see here, in this diagram that I took for the source rock, this is the line that I took for the source rock. That means all rare earth elements are twice enriched relative to the quadrant normalized. Now when I melt it, both being incompatible, the melt should be above this line. Right? But lanthanum will be more strongly partitioned because the value is less than lutetium. So the liquid, the melt, will have this type of a curve. And the solid will have this type of a curve. Now you can ask me, sir, why did you put this so far and why is it so close? You remember, this is the rock, this is the melt, and this is the residue. Residue means the melt extracted melt, the depleted melt. Now you can ask me, why have you put this closer? If in the class I would have asked you the question. But here I can't ask you. So I give you the answer straight away. So, say for example, here it is cerium. Let's say the mineral element here is cerium. Now I write here N and M. Have you understood? This distance is N, this distance is M. Now, N divided by N plus M is equal to what? N divided by M plus N is what? Is F. Why? Is it not? N divided by M plus N is F, and N divided by N plus M is 1 minus F. Have you understood? Because if we have taken 5% melting, F is 0.05, then this separation, this point, which is the melt, and this point, which is the solid, and this is the original rock, say should be in the proportion of M is to N, so that this holds. Have you understood? We did this in the phase diagram, the Lever's rule. So here, N divided by N plus M is equal to the fraction of melt. And M divided by N plus M is the fraction of solid. So that is why at low degrees of melting, the solid residue will have a composition which is quite close to the original melt. Have you understood? Because of this restriction. So, the melt extracted mantle
will not change significantly in composition if you have low degrees of melting. That is why the mantle almost always appears very homogeneous. No, it is not. There are differences, but subtle differences. Why? Because the amount of melt that was generated was very small. If so, the mantle composition will change much less. The melt composition will change much more. Have you understood? Now, this will, so there are two things. One is the absolute, similarly, say for example here, ytterbium, this here should be YB, ytterbium. Again it's the same, M and N here. N divided by M plus N should give you the fraction of M. So that always will be maintained. Have you understood? If I had taken high degree of melting, what will happen? Higher degree of melting. What will happen? This curve will shift downwards. And this curve will shift downwards. But that N divided by N plus M ratio, that will control the degree of melting. It will be proportional to the degree of melting. You can't get away from it. Okay? So, as I teach you, the important point is, if I take the variation, if I take the partition coefficient value of a peridotitic mantle containing olivine, orthoperoxene and clinopyroxene, then if you melt the mantle, no matter how much, at low degrees of melting, such mantle should give you this type of pattern. Means what? LA by LU, chondrite normalized, is greater than 1. This is called fractionation. From a flat pattern, you have fractionated LA by LU, more of LA, less of LU, so that this gives you essentially the slope of the REV spectra. Have you understood? So this gives you the slope of the REV spectra, and this concentrations gives you the absolute concentration of the melt and the calculated value of the solid. Have you understood? This is very important to realize. So, if you have olivine, orthoperoxene, clinopyroxene, and if you have a mantle with a flat rare earth pattern, then the melt LA by LU should be greater than 1. That is very, very important to realize. It should be greater than 1. I will keep this diagram here and I will erase this. If now I conceive another diagram here, I take the same value to chondrite to Cn of the original rock, and I take this as lanthanum and take this as lutetium, but I use a garnet peridotite with a lot of garnet. Let's say with a lot of garnet. What will happen? I asked you to keep that diagram. KLU will be less than 1. But K of lanthanum of that high pressure garnet should be greater than 2. Have you understood? Should be greater than 2. Tell me, have you understood? The partition coefficient of lutetium should be less than 1. I gave you the table before. I asked you to give a printout. But partition coefficient of lanthanum is less than 1 and partition coefficient of lutetium is greater than 1. So, what will happen? If partition coefficient of lanthanum is less than 1, then the light rare earth elements will be partitioned into the melt. Yes? But the heavy rare earth element like lutetium or ytterbium, they have a partition coefficient greater than 1. So this will cause the melt to be depleted in heavy rare earth elements. So what will happen? From this primordial mantle source, your curve will become like this for the melt. Why? Because La is less than 1, Lu is greater than 1, so lutetium will be held back in the mantle and lanthanum will be released into the melt, so you will have a steeper slope. And if you do that, then your graph for the corresponding solid will be like this. This is for the residual mantle. This is for the residual mantle. That is important. This is also, this one will be for the residual mantle. And again, for a particular element, whichever that element is, could be lanthanum, could be cerium, could be any element. This is M, like this, I will make it the same. This is M, and this is M. So M divided by M plus N should be the fractional melt. So this will be larger, and M divided by N plus N should be smaller. Similarly, if there is an element here, then you can see N will be here and M will be here. It has reversed. At this point, you can ask me, sir, what happens here? When there is a crossover, it will be a crossover. Nothing will happen there. Why? Because there K is equal to 1. Because if you are crossing over from less than K to greater than K in garnet, so at some point of time, you will be crossing K is equal to 1. So if you cross K is equal to 1, there is no partitioning. There is no partitioning there. That is the most important thing. So what is happening here also, you will have lanthanum, if you have a garnet peridotite as your source mantle, then lanthanum by lutetium, chondrite normalized, should again be greater than 1. That means to say that your basalts that you generate from the non-garnetiferous peridotitic mantle or for the high pressure garnet bearing peridotite, lanthanum by lutetium chondrite ratio is going to be greater than 1. The only important thing is, for garnet bearing peridotite, this value will be much, much larger than this value. This value will be much larger in magnitude than this value. Why? Because the differences in partition coefficient are stronger. Have you understood? That is very, very important to realize. Always realize that when you are partitioning a rock, I have mixed it up. Actually, this point should coincide with the source rock. You can understand this. This primordial mantle, this, when the intersection occurs, the intersection will occur on the line. But anyway, this you can understand. So this gives you the Mn is to N ratio, melt is to solid, and there will be a reversal here because this now becomes a solid and this becomes the melt. Now there is an important point to say. I told you all the mantle derived melts therefore should be technically high pressure mantle or low pressure mantle melting should give you lanthanum by lutetium chondrite normalized should be greater than 1, but for high pressure mantle and the garnet peridotite, it should give you a ratio significantly larger than 1. Significantly larger than Have you understood? Now we go to the very last point here. Last point. So, now just before we go into the last point, I can tell you that lanthanum by lutetium ratio of mantle derived melts should be greater than 1. But there is a condition. What is the condition? That the primordial mantle has a flat slope. Here, La by Lu for this mantle, what is the value of La by Lu? See, La is 2Cm, twice quite normalized. Lu is equal to twice chondrite normalized. La by Lu, chondrite normalized, is equal to 1. Of course, because both of them have the same condition. So when I drew these diagrams, I did it where La by Lu chondrite normalized is equal to 1. That means the mantle was not fractionated before. Not fractionated. That's a very important part. And it was only twice enriched with respect to the chondrite. But twice enriched with respect to was equal to 1. That was the source rock was not fractionated. Right? Good. Now, we go over to the last plagioclase and then we will switch over to something which will be very difficult for you now to prove. Anyway, let us see this. Once again I draw the diagram and once again I draw it here. Okay? Draw it here. The primordial mantle 2Cm. This is lanthanum, this is lutetium. Now you see, if plagioclase was in the source rock by a large amount, have you understood? So, the plagioclase in the solid would be this is how it would be. And what about the melt? It would give you a complementary signature. So this, if this is the source, if this is the unmelted rock, if this is the unmelted rock, this is residual rock, and this is the melt, then this is what it would be like. So the rock, and you know, at any point, it should satisfy M is to N. At any point, any element, it will satisfy M into N. In fact, this will go up a little bit and this will go down a little bit. This will go up a little bit and this will go down a little bit. So now, what will happen if you have plagioclase, La by Lu chondrite normalized should be less than 1. In the melt, La by Lu chondrite normalized should be less than 1 because lanthanum and lutetium are both incompatible, but lanthanum is less incompatible. So lanthanum will be released less into the melt, whereas lutetium, the fractionation of lutetium will be very high. And europium here would be held back in the residue, so this will develop this type of anomaly. Now this is called negative europium anomaly. Negative europium anomaly. This is given, but if EU3 plus was there, I told you this would have been here. If it was EU3 plus, this would have been here. If it was EU3 plus, it would have been here. So EU3 plus divided by EU2 plus, EU2 plus by EU3 plus, if this concentration is, this is called the magnitude of the anomaly. So for plagioclase, you will have a negative europium anomaly because that ratio will be less than 1. And here, the ratio will be greater than 1. EU2 plus by EU3 plus concentration, this will be more than 1. here it should be less than 1. So if you have if you are melting plagioclase in the mantle, then you would expect the lanthanum by lutetium to be less than 1, and the rocks will have a negative europium anomaly. Right? So now, I will place a problem for you, and let us see what you do about it. So we understand a few things from this, that for mantle derived metals, lanthanum by lutetium should be more than 1, unless the rock is rich in plagioclase. If the rock contains substantial amount of plagioclase, then the melt should give you a negative europium anomaly. Have you understood? This is very clear. Lanthanum by lutetium ratio normally should be greater than 1. If there is substantial amount of plagioclase, the lanthanum by lutetium ratio may become less than 1, but in that case, you will have a negative europium anomaly in your melt. Have you understood? If you have garnet, high pressure garnet peridotite, or you have low pressure non-garnetiferous peridotite, La by Lu in melts of garnet peridotites will be much higher than La by Lu of in low pressure melting of garnets, low pressure melting of peridotites. That means no garnets. Have you understood? And also you can realize another point, that lanthanum concentrations in garnet high pressure melting, garnet bearing melting, will be very high considered to lanthanum concentrations of melting of low pressure of the mantle. Now I will give you a plot, and I will ask you to give me an answer to this. Some possible answers. Here I am trying to plot basalts of the earth. Important, there are important are the most dominant ones are in mob. There are other types of mobs, but in mob, normal mob is the very dominant. Then you have island arc basalts, ocean island basalts, continental flood basalts. So these are almost the dominant type of basalts that you have. In mob, island arc basalts, but these are, highly contaminated by the crust. Then ocean island basalts typified by the Hawaiian Islands. And then you have continental flood basalts like you have in our India, for example, the Deccan. Now, I am drawing the graph. This is 1, 10, 100, 1,000. Rock by or I can say basalt by chondrite. And this is a log scale, remember? So the divisions become smaller as you go up and down. And this is lanthanum, and this is lutetium, and somewhere here you have europium. These are N-mobs. these are in moles. Does it push you back? And then you have a wide range. Let me not distinguish. Let's go into the major problem here. This is OIBs and continental flood vessels. These are two fields. Dominant, I have ignored Isla dark basalts because of certain reason. But this is a pattern more or less followed. Here, if you plot ocean island basalts and continental flood basins, it's like this. And if you have normal mob, they are like this. Some with a small, what am I doing? Small European anomaly. Now here, for the normal mob, LA by LU, CN is less than 1. That is damaging. Because what we taught was that LA by LU chondrite normalized should be greater than 1 for all. And here I see LA by LU chondrite normalized is less than 1, and most of them below 10 cl. 10 cl. This is this slope. But OIBs and CFBs, their lanthanum by lutetium ratios, chondrite normalized, is greater than 1. Now, if this is so, then I leave it to you to think how this can be done. Okay, just before we end, let us think about possibilities. How about this? You can say that I think it could be, one possibility could be that these are products produced by high pressure melting of a garnet peridotite. High pressure melting. You see, I am not now, let's discuss assuming a chemically homogeneous mantle. If you bring in that there is a mantle which is chemically heterogeneous and then you don't know what is what, you will not be able to do anything. So, let us think that we have a chemically homogeneous mantle. Not the mineralogy, chemically, the composition of mantle, wherever you break, they will have the same composition. Let's start with that. If we do that, this would definitely imply high pressure melting of garnet. Now, if it is high pressure melting of garnet, you don't expect plagioclase to be there. Because, as I have showed you in the diagram, plagioclase occurs a very small field. A very, very small field near the dry solidus. So is spinel, and it's at the lowest pressure. And spinel also is a very small field. If this is like this, then we can think that ocean island basins and continental flood basins are formed by high pressure melting of metal. Low degrees of high pressure melting of metal. How will you talk about this? How will you explain this? How will you explain this? If it was a chemically homogeneous metal. Before I end here, I want to say you one thing. I played a trick on you. Maybe those who have been intelligent have picked it up. But I must tell you, I played a trick on you. When I took the rare earth element, I always took a flat rear arc pattern. Do you understand? I took always a flat rear arc pattern. Remember, I took LA twice chondrite, LU twice chondrite, LA by LU chondrite normalized 1. That means I always took the rock as there is chondrite normalized concentrations, but one and the same across the whole spectra of the rear arteries. But imagine if the mantle was fractionated before. If the mantle was fractionated before, that means I am saying to start with the rock LA by LU chondrite normalized is not equal to 1. Then what would have happened? Then what would have happened? Have you understood? Then what would have happened? But because here, as I see, LA here in this diagram, LA by LU is less than 1 for the mantle. Have you understood? Now if you do that, then and you melt it, okay, I will leave it to you to think. I want your MTech students, you're not second year students whom I teach. You're MTech students, you have been taught something, you have read something. I'm just giving you this as a clue. Is it possible to have a basalt like this? Normal mobs, remember normal mobs? The whole ocean floor is a normal mob. Is it possible to explain this by taking a mantle which does not have a flat rear arc pattern? It does not have. LA by LU is not 1. Chondrite normalized is not 1, but has a different value. But the rest of it will work. The rest of it will work. Is it possible to explain more? Now, if I have this type of a mantle, it cannot be just like that, because the chondrite has a flat pattern. So to start with, a mantle started with a flat pattern. But it is possible that a mantle by one set of melt extraction became inclined, this I showed you before, just now before. The residual mantle was showing a strain like this. Now, is it possible to remelt the residual mantle? Remelt the residual mantle. So you already start, for your first phase of melting, you had this to start melting. And then you produced the residual mantle, and you remelted the residual mantle. So that means, can you conceive if your normal mob would require 2 stages of melting? So here when you produce, you did not use a mantle with LA by LU equal to 1 chondrite normalized. You started with LA by LU not equal to 1. This I leave it to you. Okay, thank you.